Okay, so we're back with linear transformations. When we left off last time, we had really only talked about this definition of a linear transformation. And I was saying at the beginning of the video that our main goal of linear transformations in the first place is so we can completely generalize the idea of a function. But you may have noticed a couple problems that keep us from completely generalizing the idea of a function. So the first is these. So in this definition, instead of being able to go from just any arbitrary vector space to another, we're just allowed to go from Rn to Rm only. So what about the other spaces that we've been working with in this course? So, why can't we go from polynomials? What about vectors with complex entries, stuff like that? So this is, one of the first things that should bother you a little bit about this definition. And then the other one, this one's more important, are these here. So as we talked about last time, these E1, E2, ENs, these are the standard basis vectors of the vector space Rn. But this is a problem because you're assuming that the Rn that they give you here is written in terms of a standard basis. What if it's not? What if they give you a completely random basis that's not standard? Then this definition just falls apart. So that's our second issue here. Only given a definition in terms of a standard basis, which is kind of bothersome. So what we're going to do now is we're actually going to combine a little bit about what we know about change of basis matrices in with our understanding of linear transformations, and we're going to actually be able to generalize this a lot further. So I'm going to go ahead and write down this definition, and it's going to look really scary at first, but we're going to work through it. We're going to see it's actually two separate things we know how to do independently, so we might as well be able to do them together. So to generalize this definition more, I'm going to assume that I just have a random vector space V and another random vector space W. So these are vector spaces, and it's going to have a basis given by V1, V2, all the way up to Vn for V. And then W is also a vector space with a basis. I'm going to call it W1, W2, up through Wm. So notice here that N and M don't necessarily have to be the same size here. So I've preserved the concept that they can be different sizes, which is good. So then if T, I should mention also that these are just arbitrary basis vectors, right? So it's not necessarily the standard basis that I've defined for V and W. So everything that we had a problem with so far up here is taken care of, but what we end up with then is something a little scarier. So if T going from V to W is a linear transformation, all right, now don't freak out. Then T, so different notation, we'll explain what this means in a second. T from B to C is defined as T of V1 with respect to C, T of V2 with respect to C, all the way up through T of Vn with respect to C. Okay, and what's this called? This is the matrix representation relative matrix representation of T relative to the bases B, and C, right? Okay, so that's the full name. Imagine that being your name. And, but it takes care of everything we need to. So we have, arbitrary vector spaces here. We have arbitrary basis vectors. They are different sizes. Everything seems to work out. It's completely general, which is fantastic for us. But it looks daunting. So let's go through this definition here piece by piece, and let's see what's actually going on. So what I want you to do for a second, I'll erase these temporarily. I want you to ignore the brackets on the outside with the C, okay? So with respect to C, here and here and here. So when I was, doing this in recitation, I just covered them up with my hand, but alas, here we are. So we're not doing anything different than this first definition, right? All I'm doing is I'm sending through some vector here. I'm sending that vector through T, and then I'm sending this vector through T, and then I'm sending that vector through T. In this case here, these happen to be the standard basis vectors. Here, these are just the random basis vectors they give us. So my first step is to find T of V1, T of V2, T of Vn, right? So I'm going to go through, and all I'm going to do first is I'm going to send through all of these basis vectors here. Okay, great. Then what I have to do, I'm going to draw these back in here. I have to write each of these in terms of the basis C. So I have to write them referring to the T of V1, V2, and Vn's in terms of the basis vectors of C. And how exactly do we do that? Well, we learned a bit about how to do it with change of basis matrices, but just in general, if you have a vector, let's just do an example, and then we'll see it via example what you have to do. Okay, but the important thing is we know how to do this, right? We know how to send through vectors. That's nothing different than what we've been doing in the first part. And then we also know through change of basis how to write vectors in one basis in terms of another one. So my point here is that even though this looks super scary here, we're actually able to do two independent things pretty easily and combine them at the end. All right, so let's do an example. It's a bit of a long example, and I have it copied from the textbook. Find T from B to C relative to the given ordered bases. So it's somewhere at the bottom of the page. I'm going to bring it up. So hopefully this works okay. Nice. Look at me learning how to use an iPad. Okay, so we're given two parts of the problem. We're given a basis, or two bases, B and C, that correspond to the vector spaces V and W. You'll notice the first one here. Oh, I can't write in here. Okay, I lied. In part A, there we go. These are the standard bases. So our vector space V is the second degree polynomials. So these are polynomials of degree 2 or less. And then W is just going to be R2. So you'll notice then that the basis they give us B is the standard basis for second degree polynomials, and the basis they give us C for W is just, the standard basis vectors for the coordinate plane. So this takes us back to our original definition, but to keep us, on topic, I want to use the scary definition anyway. So we go through, we'll go ahead and go through that now. So what I need to do first, remember, I need to find t of v1, t of v2, and t of vn. So so t of v1 then is equal to t of my first basis vector of b, which in this case is 1 plus 0x plus 0x squared. So I'm just taking what they give me first inside of the curly braces of b, and then I literally plug in 1, 0, and 0 for a, b, and c respectively, and this gives me 1, 2. I take t of v2 is t of 0 plus 1x plus 0x squared, which gives me 0, 1. And then t of v3 is equal to t of 0 plus 0x plus 1x squared. It's my third standard basis vector, and that gives me -3, -2. Okay? So I found t of v1, v2, and v3 pretty easily. Now what we have to do is we have to put these in terms of the basis vectors they give us in C. So put these in terms of C. So how do we do that? Putting a vector in terms of another basis, what you have to do is you have to take your vector. So I'm just going to use 1, 2 as an example. And then what you have to do is you have to figure out exactly how you would use the basis vectors from C to write this vector here. So I would say it's something like C1 times the first basis vector, 1, 0, plus C2 times the second basis vector, 0, 1. So it's just important to know where these are coming from. These are the basis vectors of C. All right, and then what you have to do is you have to solve for C1 and C2. In this case, it's the trivial, well, not the trivial solution, but it's very easy. You know that C1 has to be 1 and C2 has to be equal to 2. So then you know that T of V1, written with respect to the basis C, is equal to the vector 1, 2, written with respect to the basis C. But we just found that here to be exactly equal to 1 and 2. So you may be thinking, why is this so easy? This seems pretty dumb to be doing. It's because we're working with the standard basis vectors. So they gave us, 1 x and x squared, and then the 2 coordinate vectors there. You're not going to get anything really weird out of case, or the part A that we're working on now. And so we can go ahead and just finish this problem off. T of V2 with respect to C is, 0, 1 with respect to C, which, because we're working with standard basis, just the vector itself. T of V3 with respect to C is -3, -2 with respect to C, which gives us -3, -2. Great. And so what we do with these now is we stick those in as the columns in our matrix, right? Like this, like that, just as we did in the previous video. So then the, what's this thing actually called? The matrix representation of T relative to the bases B and C is equal to 1, 2, 0, 1, -3, -2. And we're done. Okay, so that's part A. The reason we were able to whip through it so quickly, again, standard basis. Let's do part B. B is a lot more interesting. So B, I'm going to rewrite the bases so I don't have to keep going up. The basis B they give us is 1, 1 plus x, and 1 plus x squared. The basis C that they give us is 1, -1, 2, and 1. 1, -1, 2, and 1. Okay. So, this is a little more spooky because we don't have standard basis, but we're going to do the same process. So first, we're going to find T of V1, T of V2, and T of V3. So we just send them through. T of V1 is equal to T of 1 plus 0x plus 0x squared. And I'm just writing this out to be very thorough, is just what we got in the first case, 1, 2. T of V2 is T of 1 plus 1x plus 0x squared, which gives you 1, 3. And T of V3 is equal to T of 1 plus 1x plus 1x squared, which gives you negative 2, 1. And I know you can't see the transformation. I didn't think about that. But you can take my word for it. And that's really the only part we need this anyway. Okay, so I found the T of V1, V2, and V3. Now I need to write these in terms of C. So again, I take my first vector here, 1, 2. It's going to be C1 times the first basis vector of C plus C2 times the second basis vector of C. And that's these here. So they're no longer standard basis. 1, negative 1, 2, and 1. And so at this point, you're working with a 2 by 2 case. You have a couple of options. You can actually just eyeball it. So in this case, if you see that C1 is negative 1 and C2 is positive 1, I believe you get an answer here. So then that tells me that T of V1 with respect to C is equal to 1, 2 with respect to C, which we just found to be negative 1, 1. So that works in this particular case, but let's take a look at the second vector, 1, 3, is equal to C1 times 1, negative 1, plus C2 times 2, 1. And you can look at this and you can think about it for a bit, but you're not going to want to just be thinking for minutes about this on an exam. We're actually in a perfect position here to set up a matrix. So I'll take one more step here to show you exactly what's going on, but I can take C1 plus 2C2 from the top line and set it equal to 1. And then I can say minus C1 plus C2 is equal to 3 from the bottom line. Now this is something we can solve from Algebra 2, right, if we really wanted to. But there's no point in learning Chapter 2 all about matrices if you're not going to use them. So you might as well set up this matrix 1, 2, minus 1, 1, augment it with 1 and 3. And then we can use row reduction to solve our system of equations. So let's take one step. Let's do R2 is equal to R1 plus R2. So I have 1, 2, 1. Top row stays the same. The bottom row becomes 0. 2 plus 1 is 3. 1 plus 3 is 4. At this point, I don't feel like finding the reduced row echelon form. I'm just going to stop and use back solving to get it. So I can read off my system of equations. So I have C1 plus 2C2 is equal to 1, and then 3C2 is equal to 4. So at this point in time, I can solve it pretty easily. I can say that C2 has to be 4/3, and then C1 is 1 minus 8/3, which gives me negative 5/3. Okay, great. So then that tells me that, T of V2 with respect to C is just my vector 0, 1 with respect to C. No, sorry, it's not 0, 1, it's 1, 3. I was looking at the wrong thing. It's this vector here, 1, 3, with respect to C, which we just found to be negative 5/3 and 4/3. So this was a case you really couldn't just eyeball it as much as you would really want to. And then we'll see it's the same for the third vector as well. So we've done these two. Now we have negative 2, 1. Let me make sure I wrote that down right. Yep, negative 2, 1 is C1 times my first basis vector, which is 1, negative 1, plus C2 times my second basis vector, which is 2, 1. Again, I'm just going to go and solve this system. I'm going to skip straight to the augmented matrix here. So I have 1, 2, negative 1, 1, negative 2, and 1. You can solve the system of equations the same way. Row 2 is row 1 plus row 2. You get top row remains the same. You get 0, 3, and negative 1. So my system of equations now reads C1 plus 2C2 is negative 2, and 3C2 is negative 1. Okay, so C2 is negative 1/3, and C1 is negative 2 minus, or plus 2/3, which is minus 4/3, I think. Yep, cool. So that tells me then, finally, that T of V3, written with the basis C, is the same as negative 2, 1 with respect to C, which we just found to be negative 4/3, negative 1/3. Okay? So lastly, we can collect all of our vectors that we had. So we have this one here, I think, right? Yep, this one here, negative 1 and 1, which forms our first column of T, B, C, negative 1, 1. We had our second one was right here, negative 5/3 and 4/3. And then our last vector here, negative 4/3 and negative 1/3. And now you're done. Okay, so you can see they can be really mean to you and give you not a great basis to work with, as they did in part B. So it's a lot of computation, but in the end, you get your result here, and that's pretty much all you have to do. The rest of the textbook section covers some cool stuff about how these work with inverses, if you're interested in that. But that's all for this video.